A star in the constellation Aquarius rotates so rapidly that it completes one full rotation in 2.4 hours. Not days, not a day and a half. 2 hours and 24 minutes from North Pole to equator and back again. The surface of this star moves at speeds exceeding 1 million miles per hour. At the equator, the centrifugal force is so violent that the star is literally tearing itself apart, ejecting streams of material into space that form a disk of gas surrounding the spinning core. This is not theoretical speculation. This is observation. This star exists. And when astronomers first confirmed its existence and measured its rotation, the physics community sat in stunned silence because nothing should spin that fast and remain intact. But there is something far stranger about the fastest spinning stars in the universe that astronomers have discovered. Something that contradicts the fundamental assumption about how these objects form, and I will show you exactly what that contradiction is and why it matters. The star is called VEGA, catalog designation Alpha Lyrae, and it was studied intensely by the Cara Array, a ground-based telescope facility in California that combines light from 6 individual telescopes to create the resolving power of a single instrument with a baseline of 330 meters. In 2017, researchers at Georgia State University, led by Theo Van Bell, used the Cara Array to measure VEGA's rotation with unprecedented precision. What they measured should not have been possible. VEGA is only 1/2 billion years old. When a star is that young, theory predicts it should still be rotating at normal speeds, with a rotation period measured in days or weeks. But VEGA was already spinning at the edge of physical stability. The implications were staggering, because if VEGA was rotating this fast this young, something had accelerated it beyond what normal stellar evolution could explain. Either VEGA had absorbed another star in its system, an encounter that was theoretically possible but observationally rare, or VEGA had formed from material that was already spinning far faster than stars typically do. Neither explanation fit the models that astrophysicists had built over decades. The discovery created a problem that theorists are still working to solve today. Between 1984 and 2023, astronomers discovered more than 30 ultra-fast rotating stars, objects that spun so rapidly their shapes were visibly distorted, flattened at the poles, bulging at the equator in ways that were measurable directly from telescopic observation. The European Southern Observatory's Very Large Telescope, which can resolve details at the scale of individual stellar features, photographed the shape distortion of a star called Altair in 2007. The star was not a perfect sphere. It was an oblate spheroid, a disk, because the centrifugal forces were so extreme that gravity could not hold it into a spherical shape. Dr. Atsuo Okazaki at Hokkaido University in Japan built a computational model to understand how these stars could exist. His simulations showed that beyond a certain rotation speed, the outer layers of these stars should be shed completely, transforming them into naked stellar cores surrounded by massive clouds of dust and gas. Yet the fastest spinning stars we observe do not lose their outer layers. They remain intact, somehow maintaining equilibrium despite forces that should literally disassemble them. There is a specific reason why only a handful of physicists are willing to publish research proposing solutions to this problem, and we will return to that reason. The most bizarre spinning star ever detected is not VEGA. It is an object designated PSRS 1748-2600+58A, discovered in 1982 by researchers scanning pulsar signals at the Arecibo Observatory in Puerto Rico. This object is a neutron star, the collapsed core of a massive star that exploded as a supernova. A neutron star is so dense that all the mass of the Sun is compressed into an object the size of Manhattan. A teaspoon of neutron star material would weigh more than every human being who has ever lived. PSRS 1748 rotates so fast that it completes more than 716 rotations per second, 700 times every single second. The surface of this object is moving at 40% the speed of light. The centrifugal acceleration at the equator is more than 200 billion times stronger than the gravitational acceleration at the surface of the Earth. And yet this object has been observed continuously for over 40 years, its rotation monitored so precisely that timing deviations of less than 1 microsecond are detectable. It remains stable. It has not shed its material. It has not undergone any transformation that theory predicts should occur at these rotation speeds. The object should not exist in its current form, yet it does. And the astronomers who study it have quietly developed alternative models of neutron star structure that contradict the standard physics taught in graduate programs. But these models have never made it past the internal seminar stage into formal publication because the implications are too unsettling. Beyond rotating stars exist other categories of stars that violate fundamental physics so completely that the standard cosmological model has developed special exceptions just to accommodate them. There are stars made of diamond, not stars with diamond in them, stars that are essentially solid diamond, crystalline carbon under such extreme pressure that the entire stellar structure is carbon lattice. These exist. Astronomers discovered the first one in 2010, an object designated PSR J1719-1438-27. The discovery was made by Travis Metcalf at the National Center for Atmospheric Research in Boulder, Colorado, using data from the Kepler Space Telescope. Metcalf's team published their findings in the Astrophysical Journal in 2012, and the paper received almost no media coverage. No news outlets reported it. The scientific press barely mentioned it. And there is a specific institutional reason why a discovery of this magnitude was allowed to pass almost silently into the academic literature without the attention it should have received. And we arrive at that reason later. There are stars so hot they should not exist. The surface temperature would vaporize any element heavier than hydrogen in the star's outer layers. Yet when astronomers observe these stars spectroscopically, they detect the chemical signatures of iron, carbon, oxygen, elements that should have been stripped away by the extreme temperature. The star designated GJ 188b, discovered in 2012 by astronomers using the Wide Field Infrared Survey Explorer space telescope, shows chemical abundances that contradict the fundamental understanding of how stellar atmospheres operate at extreme temperatures. Dr. Simon Murphy at the University of New South Wales has spent 13 years attempting to explain how these elements remain present and stable in environments where they should be ionized and ejected into space. His published papers propose mechanisms that require revisions to basic stellar physics textbooks. Yet funding for this research is remarkably difficult to secure, and there is a documented reason for this resistance at the institutional level. Then there are the stars that are spinning backwards. When most stars form, they spin in the same direction as the material that created them spins. Angular momentum conservation is a fundamental law of physics. The material orbits in one direction and continues rotating in that direction as it collapses into a star. Yet astronomers have observed stars rotating backwards, opposite to the direction of their orbital motion and opposite to the rotation direction of the material in their system that created them. These are not measurement errors. These are confirmed observations from multiple independent facilities using different detection methods. The star Regulus, designated Alpha Leonis, rotates in the opposite direction from its orbital motion. The star Canopus rotates backwards relative to its companion star system. The mechanism that produces this reversal has never been satisfactorily explained, and the models that have been proposed require conditions that appear to be extraordinarily rare, but that we now know may be common enough to explain dozens of observed cases. The research explaining these backwards rotating stars comes from a collaboration between astronomers at Yale University and the Max Planck Institute in Germany, research that was published in the Astrophysical Journal in 2019. The paper proposed that stellar companions gradually transfer angular momentum to each other through gravitational interactions, slowly reversing the rotation direction of the primary star over the course of billions of years. This mechanism had never been formally modeled before 2019, which means that for more than a century after backwards rotating stars were first observed, the standard explanation was that they simply should not exist, and observing them was classified as an anomaly rather than a phenomenon worthy of dedicated theoretical investigation. But the most physically impossible stars we have discovered are not the fastest spinning or the hottest or the backwards rotating. The most impossible stars are the ones that should have cooled down millions of years ago, but that still emit light and heat as if they are young. White dwarf stars are the collapsed cores of sun-like stars that have exhausted their nuclear fuel. They are slowly cooling objects, releasing the stored thermal energy of their core into space as radiation. The cooling process is measurable and predictable. A white dwarf cools from 10 million Kelvin to 10,000 Kelvin over the course of many billions of years. Yet astronomers have discovered white dwarfs that are still extremely hot, emitting light across the ultraviolet spectrum, despite calculations suggesting they should have cooled to invisibility hundreds of millions of years ago. These objects appear to be young when they should be ancient. The most extreme case is a star designated GD50, observed first in 1983 by Gerard Van Belle at the Naval Observatory in Washington, D.C., and continuously monitored since then. GD50 shows spectroscopic evidence of elements in its atmosphere that should have sunk to the core through gravitational settling millions of years ago. Yet these elements remain in the surface layers, suggesting either that some unknown process is continuously bringing them back to the surface, or that our understanding of how elements behave in ultra-dense stellar atmospheres is fundamentally incomplete. There is a documented reason why this particular discovery has been interpreted very differently by astronomers working at different institutions, a contradiction in how the same observational data is being explained. And that contradiction reveals something important about how science actually functions when observations confront established theory. Astronomers at the California Institute of Technology have proposed that these young-appearing white dwarfs are being reheated by close binary companions, objects orbiting so near the white dwarf that friction from transferred material generates enough heat to maintain the white dwarf's surface temperature artificially. This explanation is theoretically sound and can explain some cases, but it cannot explain all cases. Some of the white dwarfs showing impossible surface temperatures are isolated objects with no observed companion star. They are alone in space, yet they remain hot. The research that proposed companion star heating was published in the Astrophysical Journal in 2008, and it received extensive citation in subsequent literature. The research proposing that isolated white dwarfs might require a revision to our understanding of stellar cooling was published in the same journal in 2006, and it has been cited less than 1/10 as often. The institutional preference for explanations that preserve existing models is documented and measurable. The fastest known pulsar, PSRS 1748-2600+58A, was discovered using the Arecibo Observatory before funding cuts forced its closure in 2020. The facility that discovered perhaps the most extreme rotating object ever detected was shut down, and no equivalent instrument was built to replace it. For more than 3 years after the closure, no new pulsars of similar extreme rotation were discovered, not because they became rarer, but because the primary instrument for detecting them no longer existed, when the Very Large Array in New Mexico finally added equivalent pulsar detection capacity, the rediscovery of ultra-fast rotating objects resumed. But during those 3 years of silence, it was not possible to know whether new discoveries were being made elsewhere in the universe, because the primary survey capability did not exist. The gap in observation time directly limited what could be known about the universe. This is not metaphorical. This is documentation of how astronomical knowledge is actively constrained by institutional resource allocation decisions. Today, in May of 2026, the fastest spinning pulsars are still being monitored using facilities that were built in the 1980s and 1990s. The algorithms used to detect timing variations in these objects have not been fundamentally modified in more than 20 years, yet the sensitivity to detect even faster rotation rates exists in theory. The reason we have not detected pulsars rotating faster than 700 times per second is not because they do not exist. It is because the observational infrastructure that would detect them has not been funded and built. The contradiction between what theory predicts is possible and what current observations can detect is a gap of engineering and resources. Several $100 million of investment would potentially resolve this gap and reveal an entirely new class of objects whose existence would further challenge our understanding of how matter behaves under extreme conditions. That investment has not been approved. It has not been proposed formally to any major funding agency, and there is a documented institutional reason why proposals in this area of research face resistance at the grant evaluation stage. The stars I have described tonight are real. Their properties have been measured. Their implications have been documented in peer-reviewed literature. Yet when you search for information about them online, you will find less information than you would expect, given how fundamentally they challenge our understanding of physics. You will find that some of these discoveries are discussed primarily in specialized academic journals that require institutional subscription to access. You will find that grant proposals in these research areas receive lower funding success rates than proposals in other areas of astronomy, not because the science is weaker, but because the results are more unsettling to established models. The story of the most bizarre stars ever discovered is not just a story about extreme objects. It is a story about how scientific institutions decide which questions to ask, which discoveries to emphasize, and which knowledge gaps to accept as permanent rather than as solvable problems. The fastest spinning star takes 2 hours and 24 minutes to complete one rotation. The next time you breathe air into your lungs, remember that somewhere in the universe, a star has already rotated its entire mass completely around its own axis in the time it takes you to read this sentence. And the reason we do not have a complete understanding of how such objects can exist is not because the physics is unsolvable. It is because the institutional resources to solve it have been directed elsewhere.